Okay, start. Okay. Hello. Okay. Yeah. I'll just check if recording is being done. Right. Okay. Okay. Welcome everyone to week 5 of. Okay. Yeah. Sorry. Okay. Okay. Let's start. Okay. Welcome. Let me just check again. Just the recording is of the meeting. Okay. Okay. Welcome everyone to week 5 of the PMRF TA session for NPTEL course Approximate Methods in Quantum Chemistry. A brief intro of mine. I'm a PhD student, PMRF, in the Solid State and Structure Chemistry Unit, SSU, at Indian Institute of Science, ISC Bangalore. And I'm an NPTEL PMRF TA for this course. Just 1 minute. Just okay. Sorry about that. So I'm an NPTEL PMRF TA for the Approximate Method in Quantum Chemistry course, and we are having this PMRF TA session. There are total 8 sessions, and today it is week 5 of the sessions. Okay, so so in this week we are going to solve some problems related to week content of the week 5 of the course, which includes degenerate perturbation theory and also some questions on stator determinants. Okay. So let's just okay. Let's go to our first problem of today. All right. So yeah, the first problem is, what is the first order correction to the energies of a double degenerate pair of orthonormal states? So this is basically the simple degenerate problem that we had, and so what is given is we have to find a first order energy correction to the energies of a double degenerate pair of orthonormal states. So we are considering a pair of orthonormal states. So what will be our method to solve this question? So what we are going to do, we are going to set up the secondary determinant and solve it for the energies by expanding it and looking for the roots of the resulting polynomial in E Now it is given that because okay, we can see that it is given that because the pair of states is orthonormal, we will have S KL will be equals to del of KL. So they just briefs what is the method we generally use for this kind of orthonormal sets. In the lectures also most of the all the cases we have done for the orthonormal case. So for example, let's say we have these two states given by psi1 of 0 and psi2 of the zeroth order. These are doubly, so we have a given it is a double degenerate pair. So they have the same equal energy they give for our h cap naught, which is the without a perturbation energy. So and let's say this is h prime is our perturbation Hamiltonian. 1 minute, sorry about it. Perturbation. All right. So as we know, what we have to do is we have to make this determinant h11 prime minus E energy of first order correction, h12 prime, h21 prime, and h22 prime minus the first order correction, and we have to solve this determinant. This is our Sakura determinant, or this is the basically the Sakura determinant with this condition, because it is given that they are orthonormal. So I have explicitly mentioned it. Otherwise, like you have to put this S11, and there would be some E11 and S12 as well. But since we know that these are orthonormals, so we will not have, this will be 1 and those will be 0. All right. Now we just have to solve this determinant. So that will be h11 prime minus E1, and you multiply it by h22 prime minus E1 minus h12 prime h21 prime equals to 0. Here also, let me just define what this h11 primes are. So we know this h11 prime will be basically psi1 of the zeroth order, h prime, our perturbation, and psi1 of the zeroth order. So basically, we, in degenerate perturbation theory, we create this matrix elements for our from our degenerate states. Here we are just considering a double degenerate case. So we create this matrix elements, and then we solve this determinant, or you can see it as like just diagonalizing basically this matrix. So you just have to diagonalize this matrix, okay, and you can say other way to say it. I'll just write it in this form. Basically, whatever your perturbation is, let me write it aside. Basically, we have to write this. Whatever your perturbation is, you take the matrix element with respect to your degenerate eigenstate, and then you diagonalize it. Okay, so you diagonalize it, and that will give you, that will give you the two values. Okay, so for the first order, like it will give you two eigenvalues, and those will be your first order energy correction. E1 of 1 and E2 of 1 are first order energy corrections. All right. So you can see it like this, or which also just means that solving this determinant, which you can get from a kind of an eigenvalue equation that has been done in the class. And let me just define what h11 prime, h12 prime similarly will be psi1 of 0, h cap prime psi 2 zeroth order. Similarly, we will have h21 prime psi 2 of 0, h cap prime psi 1 of 0th order. Then we have h22 prime equals to psi 2 of the 0th order, h cap prime psi 2 of the zeroth order, right? These are our matrix elements, right? So, so this is for a general case. We don't have. I'm not writing this. This matrix element will depend on whatever your perturbation and the wave functions are. So this is for a general case how we would solve. And then if you just multiply them, let's say there will be h11 prime h22 prime, and E1 it will have h11 prime plus h22 prime plus h11 prime plus log Arabian square E1 square minus h12 prime h21 prime. So basically you will get this kind of a quadratic equation prime plus h22 prime plus prime h22 prime minus h21 prime h12 prime plus to 0. Alright, let me just check, I guess here, okay, this is right, and thus at the end your first order energy correction, so we will get two values of this quadratic equation, h11 prime plus h22 prime plus minus under root of h11 prime plus h22 prime whole square minus 4 times h11 prime h22 prime minus h21 prime h12 prime. This whole, let me just write it here actually, right, minus h21 prime h12 prime, this whole divided by 2. Alright, so this will be our first order energy correction. It will be given by this. The matrix element depends on the Hamiltonian and the wave functions. And then you can also find the when you basically diagonalize it, what will happen, as we know, our degenerate states now go instead of using this zeroth order degenerate state, it is now using some psi 10 psi 20, which were degenerate. Now we will use two different we will have some new zeroth order wave function, which will be a linear combination of this psi 10 psi 20 zeroth order, and that you can find by using this equation. Basically you will have this h11 prime, okay, you will have h11 prime h12 prime h22 prime h21 prime h22 prime times coefficient c1 c2 is equals to whatever your energy E1 is, okay, times, sorry about that, sorry, hello, अरे मैं बात कर रहा हूँ, मैं कुछ काम कर रहा हूँ, रिकॉर्ड कर रहा हूँ, okay. Sorry, recording. Okay, sorry about that. Okay, so yeah, so let me check if the recording is. Right. So we will take this even values, and we will have this like it's C1 C2. So we will have this kind of equation like H1 prime times C1 plus H12 prime times C2 is equals to whatever your variable is, and so using this kind of two equations, basically you will get this kind of two equations, and C1 plus H22 prime C2 is equals to E1 of C2. So you will have this two equations, and from here you can find C1 C2 and your this new wave function. You can say like phi of the 1 of the 0th order, that will be some C1 times psi1 of the 0th order plus C2 times psi2 of the 0th order. Okay, and then similarly like for one basically you will have two even values. You can say this is like some for the one of the even values, and from the second of the even values sorry psi 2 of the 0th order. Yeah, so you can get this two kind of combinations. Basically, so our new wave function, they are going to be basically linear combinations of this psi 1 0 psi 2 0. All right. So this is our first question. So this question just explains the basic strategy of solving this degenerate perturbation theory problems. Okay, let's go to the next problem. Okay. Now suppose that, okay, now our problem number 2. Okay. Now suppose that the potential, okay, the question is, suppose that the potential energy of a particle on a ring depends on the angle phi as h1 epsilon sine square phi. Now we have to calculate the first order correction to the energy of the degenerate ML equals to plus minus 1 states and find the correct linear combination for the perturbation calculations. Okay, so in the assignment also there was similar question. So now for this problem, basically now we have our perturbation. We have, it is given as epsilon of sine square phi. Now as we have seen in the previous question, which is for the general case, now we will need this matrix elements. So our matrix elements are going to be like this. So like I'm mentioning this as h prime h1. You can let's just go with h prime, because then we are representing. Let me just check if the recording is been done. Okay. All right. All right. So yeah, let's just represent this by h prime instead of h1, because we have been representing this with h prime. So our h prime, basically our perturbation prime is equals to epsilon times sine square phi. This is our perturbation. Now for the secular determinant, we need to find those matrix elements. So I will write them as some h prime in a general form, ml prime and ml. Okay, so we will have ml prime value and some ml value. So what we will have, I'm writing is some ml prime wave function, h prime and ml. All right, now here our, I guess, okay, we know this, how this wave function is given. So this wave function, let me just write it for psi ml. Our wave function will be given by 1 by under root of 2 pi for a particle in a length, e to the power psi ml will be given by e to the power I ml phi. Okay, so this is our psi of ml. Okay, we and we know h prime as well. So our integral this will be is equals to d phi from 0 to 2 pi. I will have 1 by under root of 2 pi e to the power minus iota okay, minus okay, let me minus iota ml. Let me just check. It is okay. I guess yeah, it is e to the power iota ml phi. Yeah. Okay. So this will be e to the power minus iota ml prime minus iota ml prime. We are getting it. Okay, yeah. So I'm writing it in this form. It is e to the power minus iota ml prime phi times our h prime, which is epsilon sine square phi, and then we have 1 by under root of 2 pi e to the power iota ml prime ml phi ml phi. All right. So this is how we will write our integral. Now I can take this epsilon and 2 pi outside. Integration will be from 0 to 2 pi. I will have a d phi, and there will be a sine square phi. So what we can do is, we know sine square phi could be written as 2 cos 2 phi. First let us bring this IML terms here. So let's just write it as minus iota, let me take common, ml prime minus, or let's just go with instead of ml, let's just go with ml value is plus 1 minus, okay, I'm going with ml primes let's go with ml prime minus ml phi. All right, it is written by this, and sine square phi, if you multiply by 2 sine square phi, so this is basic terminology, 1 minus, so we know 1 minus, it could be written as 1 minus cos 2 phi. Okay, cos 2 phi cos. All right, because cos 2 phi, let me just check myself. Cos 2 phi is cos 2 cos square phi minus sine square phi. So it will be 1 minus 2 sine square phi. Yeah, so we will have to divide it by 2. Right. So we can write our sine square phi as 1 minus cos 2 phi divided by 2. That we have written here. Right. And okay, all right, so we have written it like this. Now I can further write this as, this is just to make some integration. We will go to some easy integration. Ml prime minus ml phi. Now this cos 2 phi, now we can write this cos 2 phi as 1 minus e to the power, I can write it as e to the power iota 2 phi plus e to the power minus iota 2 phi divided by 2, and okay, and this whole is divided by 2 as well. Okay, so I have just written cos 2 phi in this form. I have written 1 minus e to the power iota 2 phi plus e to the power minus iota 2 phi divided by 2. Okay, if you open, because e to the power iota phi open as cos phi plus iota sin phi, so you can check that it is it will come as cos 2 phi. Now using this, I can bring, so there will be a 4 will come here, so let's just write it as 8 pi 0 to pi d phi, and then still ml prime minus ml of phi 2 minus e to the power iota 2 phi minus e to the power minus iota 2 phi. Alright, let me just take a minus sign because we had it will make it easy for us. Let me just take a minus sign here. We will have e to the power minus iota ml prime minus ml of phi, and this could be written e to the power iota 2 phi plus e to the power minus iota 2 phi minus 2. Alright, now just multiply this inside here, minus epsilon upon 8 pi 0 to 2 pi d phi. If you multiply this here, what we have is e to the power iota 2 phi minus ml prime plus ml. Okay, let us not take 2 phi. Similarly, you will have e to the power iota minus 2 minus ml prime and plus ml, and similarly you will have a minus 2 times e to the power minus iota, or let us take iota, let us keep the same. Just bring it here inside, so I will have basically I will have ml minus ml prime, okay, times phi here as well, integrating with respect to phi. Alright, okay, so we will get something like this. Now after we have written it like this, so here you can check that each of this e to the power iota phi integral, they will be only when whatever is written with phi, that becomes 0, we will get a 1 value, otherwise this integral will give us 0. So basically what we are going to find is we will get minus, you can integrate, so if it is come e to the power iota 0, so we just have 1 and we will get 2 pi, so we get some 2 pi times delta terms. So from each of these terms we have basically t terms, we get 2 pi times del of what you can write this as ml prime comma 2, what we have is 2 ml plus 2 plus, okay, similarly from the second term you get 2 pi times del of ml. So if I take ml prime comma ml minus 2, okay, yeah, and then you will have here minus 2 times 2 pi del of ml comma ml prime comma ml is consistent. Alright, so we will get this time. Okay, now you can take out 2 pi from here, it will give minus epsilon upon 4 times, basically we will have del of ml prime comma ml plus 2 del of ml prime comma ml minus 2 minus 2 times del of ml prime comma ml. Alright, so this is what we will get. Now we are ready to write our matrix elements. So here we have ml equals to plus minus 1, that is what we have to use. So using that, our matrix elements I can write as, okay, so I have 1 1, so it will be 1 plus 2 3, so that will be 0, that will be 0, this will give you 1 for h1 1, so you will have minus 2 and time minus epsilon 4, okay, so for you can say check like minus epsilon 4 times minus 2, that will just give you epsilon 2, right. Similarly, if you have h 1 comma minus 1 now, so for 1 comma minus 1 you will have 1 and minus 1 will be 1, so this will be a 1 and other two other second and third term will give you 0, so you get minus epsilon by 4. So we have divided by 2, I guess this should be, you will get minus epsilon by 4. Similarly, let's say you will have minus 1 term. Okay, we will have minus 1 term. The first term that will be 0. The second term del ml prime, it is minus 1 and plus 1 minus 1 minus 1, that will give us 1, and the third term will give 0. So again we will have minus epsilon by 4. And last element that we will have is minus 1 comma minus 1 prime, that will be is equals to, for minus 1 again we will have from the last term only, where ml prime equals to ml, so minus 1 can we get epsilon by 2. Okay, so these are our matrix elements. Now using this we can write and also like these are these are orthonormals. Okay, so we know that s11 and s minus 1 comma minus 1 will be equals to 1, and s1 comma minus 1 and s minus 1 comma 1, those will be 0. So the previous case, the general case where we saw. So using this we can write our determinant as epsilon by 2 minus our first order energy correction. Okay, let me just write the what we need to find, h11 prime minus whatever our first order energy correction is, h12 prime, h 21. Okay, in the matrix element basically ml values, because our matrix element is just ml h of ml prime and ml. h1 prime minus e1, it will be h1 1 minus 1. Okay, I will write this as 1 comma 1 comma 1. Let us write it in 1 comma 1 form. So we have h1 comma 1 prime minus of our first order correction, and we will have h1 comma minus 1 prime minus no, nothing minus here. Then h prime minus 1 comma 1 and h minus 1 comma minus 1 minus e of 1. Alright, this determinant we have to make 0. So again this will give us h 1 comma 1 prime. Okay, now let's just put the values, that will make things simpler. Now our matrix element we are fine. Okay, so this will give you a quadratic equation if we just go with these terms, or we can just now put the values. So h1 prime is epsilon by 2 minus e of 1, h1 comma minus 1 is minus epsilon by 4, h minus 1 comma 1 is minus epsilon by 4, and h minus 1 is again epsilon by 2. Alright, so we have epsilon by 2 minus first order energy correction minus epsilon by 4 minus epsilon by 4 and epsilon by 2 minus first order energy correction, first order correction to the energy. Then again we will get this kind of quadratic equation. This will be whole square minus epsilon by 4 whole square, that will be equals to 0. So you can see this will give epsilon by 2 minus epsilon 1. Basically we will get our energy value E1 as some epsilon by 2 plus minus epsilon by 4 from here. So we have two values. Okay, one value will be epsilon by 2 plus 3 by 4. Okay, let me just write it as plus and minus. Will be 3 by 4 of the epsilon, and another value that we will get will be from the minus sign. So epsilon by 2 minus epsilon by 4, that is just epsilon by 4. So these are our two first order energy corrections that we will get for this particle engineering problem by combining ml by combining this degenerate state ml plus minus 1. And now what will be this combination? We just need to find those the coefficients. Okay, so from here again let me just write this equation. So you have to let's write the determinant epsilon by 2 minus of whatever your energy E1 is minus epsilon by 4 minus epsilon by 4 and epsilon by 2 minus energy E1 times C1 C2 equals to 0. So just multiply it here. Equals to 0, and then you will have another equation epsilon. Okay, so one equation that we get is epsilon by 2 minus E1 times C1 minus epsilon by 4 times C2 equals to 0. Yes. Okay, we have epsilon by 2 minus E1 times C1 minus epsilon by 4 times C2 equals to 0 minus epsilon by 4 C1 plus epsilon by 2 minus E1 C2 equals to 0. Now, okay, now for E of 1 is equals to whatever E plus of 1 is from the plus sign, which is 3 by 4 of epsilon. Okay, so if we put that, if we put E1 as 3 by 4 of epsilon, we get epsilon by 2 minus 3 by 4 of epsilon C1 minus epsilon by 4 of C2 equals 0. That gives us so epsilon 1 by 2 minus 3 by 4 minus epsilon by 4 C1 minus epsilon by 4 C2, which gives us C1 equals to C2. Alright, and so for E1 equals to 3 by 4 of epsilon, we are getting C1 equals C2. You can solve the second equation as well, and we will get same result. You can check. And for E1 equals to E or minus, from the minus sign we are getting, which is epsilon by 4. Right, for this, okay, I will just put the values in the equation. So epsilon by 2 minus E1, which is epsilon by 4 times C1 minus epsilon by 4 times C2. All right. Let me write this that these are our equation 1 and 2. These are our equation 1 and this is our equation number 2. And we are using these two equations to find C1 and C2. Right. To find C1 and C2. Right. Find C1 C2, we are using these two equations. We first find it for 3 by 4 of epsilon, and the value is epsilon by 4. For epsilon by 4, it will be epsilon by 2 minus epsilon by 4 times C1, and epsilon by 4 times C2 equals to 0. And here we can say epsilon by 2 minus epsilon by 4, that will be just epsilon by 4 times C1 minus epsilon by 4 times C2 equals to 0. That gives us C1. Alright, let me just check actually. For the first one, what we are getting is C1 equals to minus of C2. Okay. So this will give you C1 equals to minus of C2. As you can check, this is C1 equals to minus of C2, and this will give you C1 equals to C2. All right, and then for normalization, okay, for normalization, mod of C1 square plus mod of C2 square, that has to be equals to 1. So here you can check that mod of C1 equals to mod of C2 equals to 1 by root 2. So basically for E1 equals to 3 by 4 of epsilon, our let's say our new phi function of the 0th order will be equals to 1 by, okay, and this is for 3 by 4 epsilon. Let's write this notation. That will be equals to 1 by root 2 times of this will be psi 1 of the 0th order minus a psi of minus 1 of the 0th order. So this is basically our psi ml for plus minus 1. So it will, so our 0th order now new ground state will be a linear combination, and it will be with for 3 by 4 epsilon energy, it will be with a minus sign. And for E1 equals to epsilon by 4, we will have phi epsilon by 4 0th order equals to 1 by root 2 times psi 1 of 0, as C1 is equals to C2. So it will be just sum of both plus psi of minus 1 of 0. Right. All right, so this is our problem number 2. So basically we first solved for a general case, and then we are able to solve for this particle inner link problem. All right. So let's move on to the next problem. Okay. Let me just check the recording is still done. All right, let's come to problem number 3. Okay, now, okay, so problem number 3, as done in the lecture, for a 3 electronic system, consider we have a psi which is given by F1, G2, S3, J4, a 4 electronic system, and determine a stator determinant, and show that the obtained wave function satisfy the indistinguishability of identical particles, satisfy it antisymmetric. So that is basically what is done in the class for the 3 electronic system, and let us do it for a 4 electronic system. So let us start from the similar manner as done in the class. So we know that, okay, we have this F, G, H, and J. We have like 4 wave functions. So this is going to be, so we know that what could be the combinations possible. They are going to be various possible combinations of this thing. For example, like we can, the first combination, let's say that is given that phi 1, G2, S3, J4. I'm not going to write because see, as for the 3 systems, we had like 3. We have like 3 question here. We have 6 combinations. Okay, we have like 6 combinations. If you remember, for the 3 electron system, how to arrange these electrons. For example, if like another combination could be, I can apply this permutation of 1 and 2 on this psi 1. Alright, so permutation of 1 and 2 on psi 1 will be F1 on, okay, so what will happen? So this operator, it will just interchange 1 and 2 operator, electrons 1 and 2. So now electron 1 in F, 1 and 2 will be changed, so F will be a 2, alright, G will be a 1, and H and J are the same. Alright, so this is another combination in which we can put our electrons in this spin orbitals. Now similarly, we can have psi cap 3, which will be 1, 3, on this psi1 itself as done earlier. So we will have, okay, now what is a psi1, and we have to do this 1 3 combination, so we have to interchange 1 and 3 now. So let me just write F, G, H and J. Now 1 and 3 will be interchanged, so F will have 3, H will have 1, and this J and H will have 2 and 4. Alright. Now, as you can see, so basically this kind of combinations, they have been done earlier as well. Similarly, we can do again, like we have 4. Now, in the 3 electron case, we have only like 1, 2. We just do 1, 2, and now we can go up to 4 on psi1 itself. So you just have to write, you can write like this, you can go whatever your psi1 was. Alright, you have to interchange 1 and 4, 1 is in this, so 1 will become 4, and instead of 4 you will write 1 and 2, 3. Alright. Similarly, now I can do similar perturbation on similar permutation on my what kind of a color. Okay, on psi1 itself we can just continue doing this. Okay, like on psi2 we can do, let's say 2 3 on psi1 itself, G, H and J. Again go to psi1, right, again go to psi1, and this time change 2 and 3. So let's just write 1 and 4 which are not changing, and now write 2 and 3. You can write this here at 3 and here is 2. So this is also a new permutations. So I guess you got the idea how to solve this kind of problems. Right, let me just check if for the 3 electron system we have like 6, if you remember in the class there were like this kind of 6 wave functions, 6 permutations and that we can make. And similarly, if you see for this 4 electron system, we can make like 4 times 3 times 2 times 1, so therefore 8 is at 24 permutations will be there. So you can check it. So there will be 24 permutations here. So this is going to be a big matrix. So I'm just gonna write it down, and again, like you can go and you can do some permutation on, let's say, some psi 6 or something, and you can do permutation some p cap 3 4 on your wave function, let's say some psi 3. Okay, so this is basically just to give you a practice, like if you have like permutations on this, so how this permutation operator work. Okay, so you just go to psi 3, and there will be like 24 combinations. So there are a lot of combinations that you can check, and we will just go with directly going with the results. So this is just for the practice of computation. So you can go to psi 3. This is our psi 3, and you have to interchange 3 and 4. So let's just write whatever 1 2 was there. So 1 was in here, 2 was in here. Okay, now you just interchange 3 4. You have 4 and 3. So again from psi 3 we got a new permutation, which is F4 G2 H1 J3, which you can check would be it might be different. So you have to check different kind of permutation. You can do this as a practice if you go on, but there, as you can see, there will be like 24 terms. So because we know that it will be 1 by under root of n factorial, which is basically 4 factorial terms, because earlier for 3 factorial we have 6 terms, 3 factorial terms. Now we will have 4 factorial terms, so we will have 24 permutations in here. All right. So from here, as we have seen in the 3 electron system, so our wave function phi will be some combination of I equals to 1 to like 24 Ci times psi I. So all the possible 24 combinations, we will take a summation, and that signifies our indistinguishability. So so we are just making everything what we did for the 3 electron system just seeing it from the 4-electron system, and it also helps us to understand this permutation, also how to operate permutation operator on this wave functions. So we will have this kind of 24 combinations, and by this we were able, since we have written them all in this all possible combination, that's why we are so our one thing is being done, like whatever we are making the stator determinant, it will satisfy the indistinguishability. And then for the anti-symmetry, again as when we interchange one electron, then there will be a minus sign. So whatever your C2 will be, so C2 will be minus of C1 as done earlier. So we will get this plus minus combinations. Again 24 terms, we are not gonna write them, but you know, and that will bring the anti-symmetry part in it. Okay, for example, like similarly, like for anti-symmetry, let's just not write, let's just write our directly now, write our stator determinant. But I guess it just repeats the same idea, like how stator determinant is indistinguishable, then there will be anti-symmetry, and the policy simple will be just write our stator determinant and get it. So our stator determinant will be under root of, we know there will be 4 factorial ways of arranging them. We will have 4 factorial, we will have determinant, and how we write that determinant, our rows are, we put electrons, and for columns are for spin orbitals. Alright, so I have my columns F, G, H and J. Alright, so I will put my columns spin orbitals. Alright, there will be a 4 cross 4 determinant. So my columns will be my spin orbitals, and my electrons will I will put in rows. So this row will be for this row will be for electron 1, this row will be for electron 2, this row will be for electron 3, and this row will be for electron 4. Alright, so this will be our stator determinant for electron wave function. And now for the anti-symmetry part. Now anti-symmetry means that if we interchange 2 electrons, if we change electron 1 and electron 2, then there will be a minus sign. So interchanging 2 electrons equivalent to changing 2 rows. All right, so since let me just write it in some different color. Now changing 2 electrons changing 2 rows. All right, so using this concept, so what will happen, if we change electron 1 and 2, if we change electron 1 and 2, so our phi, the stator determinant, now becomes 1 by under root of n factorial 4 factorial. Now this normalization constant also, it was the same idea of 3 factorial term. So So what you do is you will interchange, let's say, electron 1 and 2. So now you will have again, first write your spin orbitals. These are F, G, H and J. So your columns are your spin orbitals. And now put your electrons by row. And we have said that 1 and 2 electrons are interchanged. So now 1 electron will go in the second row and second electron will go into the first row. And this row is for third electron, this is for fourth electron. So when I say there is an interchange of within the wave function of electron 1 and electron 2 positions are interchanged, in Z determinant what I say, I have interchanged the rows, and by the property of determinant I can again interchange these rows and bring a minus sign. Okay, so let's say I write this as my phi prime, phi, or let me just write it as the Z determinant as phi 1 2 interchange. So what will happen? I can interchange this row 1 row 2 again, and by the property of determinant I will get a minus sign here. So again I will just interchange, so it will become F1 G1 H1 J1 and F2 G2 H2 J2 F3 G3 H3 J3 F4 G4 H4 J4. Alright, and it is the same as our main phi wave function. So what we are basically getting is minus phi. So we are getting a minus sign when we are interchanging we are once interchanging the electrons. Similarly, so this shows the antisymmetric. So wave function let me say this is indistinguishability, it's mentioned here. So wave function, so our wave function phi is antisymmetric. So this is antisymmetric. Okay. Now you can check in the same way, like if you are interchanging, like you are doing now the similar perturbations, this permutation that you have done, like you have interchanged 1 and 2, you can interchange 1 3. Once I have changed 1 2, I am getting a minus sign. Now if I do some let's say, okay, if I do something like this, if I do a permutation, let's say I have done 1 2, I am getting a minus sign. Let's say I am going 3 4 on this 1 2 wave function that I have. Okay, so let's just write this 1 2 wave function only. So what you can get is, okay, let us not write the minus phi, let us write this what we got in here. Okay, we got something, this matrix here. Let us write this one. So what we have is, if we interchange 1 and 2, our matrix was F2. Okay, we have, okay, let me just write that we are doing a permutation 3 4 on phi 1 2, which was 1 factorial 1 by 4 factorial, and we have like f of 2. Let me just not do 3 4 because then we have to do some, I have to show motion, but just do let's say 1 3. Alright, 1 3, that will be easy. We have interchange 1 2, we have just done 1 interchange 1 2, and now say, okay, let's just do a permutation of 1 3. Okay, so what you have in phi 1 2 was F2 G2 1 2 were interchange, F2 G2 H2 and G2, F1 G1 H1 G1, F3 G3 H3 G3 and F4 G4 H4 G4. Right. Okay, so let's just interchange one, or you can, okay, since we are taking 4, let's just go with 1 4, so that will be more interesting. Or not much interesting, but we have 4, so let's just do 1 4. So if you do this 1 4, then what will happen is you will just interchange now 1 4, F2 G2 H2 G2. Okay, I just have to change 1 and 4, so I will just write 2 and 3, whatever they are. Right, I write 2 and 3 in whatever form they are, and I will interchange 1 and 4, F4 G4 H4 J4, F1 G1 H1 and G1. All right. Now, so we are getting something like this matrix. Now, let's see what happens. Can we get it to our 5 matrix? 5 determinant. So this looks like, okay. So we know that this is giving a minus sign. So, but I started with this 1 2 determinant what we got, and from that 1 2 determinant I have applied this permutation 1 4 again. Okay, so what we expect is that since this is the antisymmetric and I changed once, I will get minus sign, and if I change again on that, then I will get again minus sign, and I should get my 5. All right. So we apply it, and then we applied 1 4 again on it, and let's just see can we get our 5 from here, and this here you can see. Okay, so now to get the 5. I can do one interchange. Let's interchange 1 and 2. So let's interchange row 1. Let me also show that. Okay, here I have changed row 1 to row 2. I interchanged row 1, row 2 and got the minus sign. Here I will interchange. Okay, I need 1 on the top. So one thing I can do it. I can just reverse the same permutation. Basically, just try to reverse the permutation. So I will interchange row 2. Okay, because I guess with this permutation we basically change this to rows. So I will change row 2 and row 4 first. So that will bring a minus sign here. Let's say row 1 and row 3, let's just write them as it is. G2, H2, G2, and in region 2 and 4, so now I will have F1, G1, H1 and J1, and F4, G4, H4 and J4. So I got a minus sign, and now I can see I just have to interchange row 1 and row 2. Row 2. Again that will bring a minus sign, so I will get plus here, and you get F1, G1, H1, J1. Okay, first write the which is not changing, which are row 3 and row 4. J4, and then interchange row 1 and row 2, which we are changing. So F1, G1, H1, J1, and we have F2, G2, H2 and G2, and since we have again interchanged one row, again we have a minus sign. So, and you can check this is 1 2 3 4, this is the same as our 5 function, our initial, and we are getting basically our okay, so we are getting our initial Saturday determinant 5. So this shows an antisymmetric. So if you do one interchange or one time you change two electron, like you change electron 1 and 2, then you will get a minus sign. If you do another interchange, whatever you are, like say again interchange 1 and 4, then you will get your same wave function. So our wave function formed by the set determinant is antisymmetry. And this is how you can apply this permutations on this set determinant as well. You have to interchange the rows. Okay, and then we have to check if it satisfies the Pauli's exclusion principle. So for Pauli's exclusion principle, okay, make two columns. Okay, now Pauli's exclusion principle is that like these electrons they can obtain just one of the spin orbitals. So for Pauli's principle, let's say electron 1 and electron 2 occupy, let's say electron 1 and electron 4 occupy same orbital f. So in that case our phi will become 1 by 4 factorial. So what you will do, since 2, 1 and 4 are occupying the same, so our first column and the seventh and the fourth column, these are because, so let's just keep the second and third column same, that will have whatever the phi was. And now what we are going to need, so what electron 1 and electron 4 occupying the same orbiter, that means column 1 and column 4 have same orbital f, because columns are for the orbital. So what we will do is our first and fourth columns we will make the same orbitals, and then we will, in the rows we will put our electrons 2, 2 and 3, 3, 3, 3 and 4, 4, 4, 4. So if I am saying electron 1 and electron 4, they occupy the same orbital. Let's just write it in, did I write this thing right? Electron 1 and electron 4 occupy same orbital f. Okay, so if I say that, then what I am saying is column 1 and column 4 of Sator determinant have same orbital f. So what happened because of this is we write the same f orbital on the first and the fourth column, G and H are the same, and then we just put our electron in the rows 1, 2, 3, 4. Now we are seeing that column 1 and column 4 are same, so this phi will be equals to 0, since two columns in the determinant are same. Alright, since two columns are becoming same, so that determinant will become 0. So from here we have seen that this So our wave function phi satisfy the so our wave function phi satisfies all its exclusion principle. Okay, this basically no two electrons can occupy the same spin orbital. Alright, because as we are seeing, if two electrons they occupy the same spin orbitals, two columns are same and our determinant 0, so we have no wave function. Electronic wave function, our electronic wave function becomes 0. Okay, so this is for the stator determinant for this problem, for basically stator determinant for 4 electrons. Let's move on to the next problem. Okay. Now, okay, next problem is calculate the energies of the calculate the energies of the foreign wave function. So we have a Hartree product given, which is psi1 alpha, psi2 beta, and which has, so basically we have a Hartree product which has we have two special orbitals psi1 psi2, and with the spin orbitals are alpha beta, so the two electrons they have anti-parallel spins. Alpha we are taking as up spin and beta as down spin. Then we have psi with the Hartree product for the parallel spin, psi1 alpha, psi2 alpha. Now why are the energies now? Okay, so we need to calculate these energies of these wave functions. So we have basically have a two electron systems, and we have to calculate the energies with respect to these Hartree products that we have. And then we have to when we see that these energies will be equal, and that is why. So why are these energies equal, and why there is no exchange term for this wave function? So this we have seen. Now we can also create a stator determinant from the above two electron wave function and show how stator determinant can show electron correlation for parallel spin but not for anti-parallel spin, and also find the energies in that case. So let us do the first part of the Hartree product, and I guess the second part you can try like it is the same thing what is done in the class, like we have proved it, but let us do the first part, and see if we will have time, then we will go to the second part. Otherwise you can try it out. That is, it is basically doing the same thing that was done in the class, but just showing it in this problem. So let us do the first part. Okay, let us do the first part. So if I write this Hartree product for this system, now let me just write the Hamiltonian. So first let me just write the Hamiltonian. So my Hamiltonian W is equals to, it will be for the first electron single electron term H1, this will be H2 plus 1 upon R12. Alright, so this will be our Hamiltonian. Now let me write my wave function. For the anti-parallel Hartree product, psi1 R1, let's say I'm writing it as omega 1, that is for just for the coordinate of spin. We have psi2 R2, we have beta omega 2. Alright, now using this, let's find the energy E1. There will be psi for this Hartree product, H cap, psi for this Hartree product. Now that will be equals to, basically I have to write this Hartree product with H1 plus H2 plus 1 by R12 for this Hartree product. Alright. Now as we can see this this element, okay, let me just write it as psi1 r1 alpha omega 1 psi2 r2, and here anti-parallel, so we will have beta omega 2 h of 1 plus h of 2 is 1 by r12. Similarly, I will have psi1 r1 alpha omega 1 psi2 r2 beta omega 2. Alright, so this you can write as psi1 r1 h of, okay, so this h of 1 we just apply on like r1 coordinates, so I can write it as psi1 r1, and here also I have psi1 r1. Alright, then we have alpha omega 1 here on and then we will have psi2 r2 psi2 r2. Alright, and then we will have beta omega 2 and beta omega 2. So this will be for h1. So we will have the similar term for h2, which will have psi2 r2 now, h of 2 psi2 r2. You will write again, you will have alpha omega 1 psi1 r1 r1 beta omega 1 beta omega 2 beta omega 2. And for r12, what we will have is we will have psi1 r1 psi2 r2, because we have both the coordinates, both electron coordinates. We have psi1 r1 psi2 r2. Alright, and spin orbitals like this Hamiltonian there, it has nothing to do with the spin coordinates. We have alpha omega 1, right, and we have beta omega 2. Alright, now you can see this, okay, so this will be 1, psi2 r2, that will also 1, this will also be 1, this will also be 1, this will be also be 1, and this will also be 1. Similarly, there is 1 and there is 1. And this r1 and use psi1 r1, these two terms, they will be equivalent, because this term and this term, they will be equal. They will be basically equivalent. Alright, because r1 r2, if you do the integral, either you take r1 or you can take r2, both of them they are just dummy dummy variables. So you can just write it as some integrating over r. But okay, sorry, but yeah, but the psi2, okay, but we have psi1 psi2, so yeah, electrons psi1 psi2 might be different, so that might get different energies. Okay, let us write it. Okay, sorry. Basically, what you get is you will get some term h11. So this is for these this matrix element h11. Then you will have h22. Sorry about that. Like the psi1 psi2 wave functions are different. So let's just keep it like that. Okay. Basically, what I was saying is that this h Hamiltonian term, that is you do integration with respect to r1, or you say it is integration with respect to r. So that will be same. And psi2 also you can write it in r2, but psi1 psi2 are different. So basically you will get some h11 element term, you get h22 plus this, if you open, so you know that this will be some kind of Coulomb term, because what we have is we have psi1 r1 here, psi1 r1 here. So if you have mod of psi1 r1 square, psi2 r2 here, and mod of psi2 r2 square, and 1 by r12, so it will be like charge density on of electron 1 and the charge density of electron 2, and charge density at position electron of electron 2, and they are interacting. So this is kind of it is a Coulomb term. So that will come as J12. All right. So this is what we are getting for our if we have up and down spins. Similarly, if you do the same calculation for E2, here now this E2 will be okay. Let me just write what is our other Hartree product is. Our other Hartree product will be psi up, basically same spins. So we have psi1 r1, alpha omega 1. Okay, we have taken alpha, and psi2 r2 and alpha omega 2. So our energy E2 will be equals to this Hartree product, h cap. Okay, I will write now h cap of 1 plus it will be h cap of 2, it will be r12 psi both up, h up alpha you can say this. Okay, and the procedure will be same, and again we know that this what will happen is that the same there's the alpha there's a spin orbital, since they will not act, and we will get 1 from there. So you can check that what we are going to get is the same thing, h11 h22 plus j of 12. So what we are seeing is that we are seeing that okay, there is no correlation, like either the spins are up or like they are parallel or they are anti-parallel, but that doesn't bring any change in the energy if we are considering the Hartree products. And why this happens? Since we know that now this is happening because now we know that Hartree approximation Hartree product, or let's say Hartree product is an independent electron wave function. Okay, so our Hartree product is basically an independent electron wave function. So basically there is no correlation. So if we do, as we have done in the class, if we do mod of psi square for any Hartree product, is just the charge the mod squares of each of the wave function that we have multiplied in the so that's why so the motion of electrons with parallel spin is not. So that is like there is no exchange term for this wave function. An exchange term is not there because of the motion of, so the motion of electrons with parallel spin is not correlated within the Hartree product approximation to the wave function. All right. So that's why we will not see correlation. And now if we make this Slater determinant instead of this, so how we will make the Slater determinant? So let us make the Slater determinant. Okay. So let's say I make a Slater determinant phi 1. Okay. So basically what we have this kind of wave function. So like I will write the spin orbitals. Let's say chi1 will be equals to psi1 r1 and alpha omega 1. Chi2 will be equals to chi2 for our first Hartree product, first kind of Hartree product where we have. So first I will make 2 electron this Slater determinant. Two electrons this Slater determinant for the anti-parallel spin. So one we will have psi1 r1 alpha omega 1, and other half we'll have psi2 r2 and beta omega 2. So these are, and that is what we have our spin orbiters. So our stator determinant for up down. Okay, so this is our anti-parallel stator determinant now I'm making, and instead of using a R3 product, just multiplying coefficient, I'm using a stator determinant. But I will have a 1 by under root of 2 factorial chi 1 of 1. Okay, so rows are our, okay, so first we will write our columns. Columns will be our spin orbiters, and the rows will be electrons 1 1 and 2 2. So we will have this phi up down 1 by under root 2 factorial chi 1 chi 2 1 and this. So this will be our stator determinant for up down for anti-parallel spin. Now what one can do is we can do a psi actually, so we can go from there as well. So okay, so sorry about that. Just stop sharing and just share again. And recording is also being done. 30 minutes, we have 30 minutes. Okay. All right. So what we can do is, okay, now we can find these energy values, and so there's like two ways, like we can find the energy values, and we can see that when we find this energy, we will get some exchange term. We will get an exchange term, or another way that is done in the class, like we can do the psi wave function, and we can see that but this is for the anti-parallel spins. So just to check, okay, we need to check about electron and show how stator determinant can show electron position for parallel spin but not for anti-parallel spins. So let's just show it using this kind of way, what was done in the class. So this is the stator determinant for the anti-parallel spins. So we have taken the anti-parallel spins. So what you can show is this correlation is that, so for this also you can show that I have written it in words, but what you can show is you can take your psi up down Hartree product and psi up down Hartree product, and if we do it again, what we see that what we get is just mod of psi 1 of r1 square mod of psi 2 of r2 square. Okay, so you will have this independent electrons, so that's why this is uncorrelated. And you can see that because that will just happen because this alpha and beta that will be 1, and basically you will have this you will have this kind of terms. Okay, or let me just write it as mod of psi up down RT product square dr1 and dr2. So we get this, and similarly for psi up RT product square as well, dr1 dr2 we will get mod of psi 1 of r1 square, same thing, dr1 dr2. So this is also uncorrelated. All right, and that's why the reason why we are not getting any exchange term. Now here also, since we don't have enough time, actually we just have 30 minutes, we will use the same technique that was done in the class. We will just actually do this instead. We will do we will find in this normalization, and but we will see that basically this mod square that is just come independent for the case if we have alpha and beta, but it will not come like that if we have both the spins same. So let's just take this letter determinant, and this is basically the similar thing that was done in the class. So you can, okay, now this letter determinant, let me just open how this letter determinant will open as this. There will be I1 of 1, I2 of 2, or let me just write it as chi A, chi B, otherwise 1 and 2 will just get confusing. Okay. Yeah. This chi of 1, chi A of 1, chi B of 2. Okay, our okay, our chi A. Sorry, what is, all right. Let me just write it again. Okay, let us define as chi A, chi B, chi A psi 1 r1 alpha omega 1, chi B is equals to psi 2 r2 beta omega 2. We have chi A, chi B, 1, 1 and 2, 2. All right. And what we will have is 1 by root of 2, chi A of 1, chi B of 2 minus chi A of 2 and chi B of 1. So this is same to what is done in the class. So you can check from the notes, since we don't have enough time. So because this is the same case that is done in the class, we have shown this. So if you do this, what you get in the end will be something like this. So you open this chi and this size and everything. So what you will get is psi 1 psi 1 of 1. You have alpha omega 1 f and alpha omega 1. Then you have psi 2 of 2 . Okay, I guess I will just since I put psi psi b, let us write them as psi psi b as well. Otherwise, again there will be some confusion. So now we will have proper special. Okay, special orbitals I am also writing as psi psi b corresponding to chi b and alpha and beta. So this could be written as half of psi 1 alpha omega 1 this, and then we have psi b of 2 beta omega 2 and beta omega 2. Then you have minus half, you will get psi of 1 and psi b of 1, then alpha. Let me just write as running like just 1 just to make it fast, into 2. Now this will be psi of 1 psi b of 1 alpha 1 beta 1 psi A of 2, psi B of 2, and psi A of 2, beta 2 and alpha 2, minus half of psi B of 1, psi A of 1, beta 1 alpha 1, psi A of 2, psi B of 2, alpha 2 and beta 2, and you will have a half of psi B of 1, psi B of 1, beta 1, psi A of 2, psi A of 2, alpha 2 and alpha 2. Alright. Okay, so this is same as done in the class. I am just writing the result here. So this will be 1. Okay, this will be 1. This will give you 0. 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 And this will be 1. And this will give you 1. So at the end, what we see is that, and this will be just the same term psi. Okay, and this two will be you are doing psi A, psi A, and psi B, and here you are doing just same psi B, but with respect to electron 1 coordinates. So that is just the dummy variable within the integration. Okay, so these two terms will be same. You can check. You can just open the integration. So this will be integration with respect to R1 vector. This and this will be the integration with respect to R2 vector. And like similarly, this will be integration with respect to R2, and this will be just integration with respect to R1, and the integration you can replace R1 with R and R2 with R, and you can see that both are same. So basically that will just give you psi A, let's say that will just give you psi A of R. Let me just write it as psi of R, some dummy variable R, psi A of R plus psi B of R, psi B of R. That is what our phi up, down, and phi up, down will come. So this is same as done in the class, so I've skipped a lot of steps. So here you can see this is just a summation of this. It will also open as a summation of this just mod square. This is just the basically the probabilities are just the addition of the probabilities of like independent electrons. So that's why this is uncorrelated. Uncorrelated for anti-parallel spin. But now let's take our same new thing. Let's take our chi c. Now take our chi B as different. Now chi will be whatever our psi A of R1, and instead of alpha, let's take alpha. Okay, we will have our parallel, so I will take both as alpha. Let's say this is also alpha omega 1, and chi B will be equal to psi B of R2 and alpha omega 2. Alright, so our phi will now, instead of making a scatter determinant, again your column will be your spin orbitals. You have chi A, chi B, then put your electrons in the row 1, 1 and 2, 2. Alright, and again I am writing the same way, I'm using the same notation chi a chi b, but now chi a chi b definitions are changed. They are for the parallel spins. Now you have chi a of 1, chi b of 2 minus chi a of 2, chi b of 1. Again we have to do the same phi parallel parallel and phi up okay, what we have find here, and the procedure will be the same. So as so it is since the procedure is done in the class, I am not repeating those terms here. Let me just write the first term, okay, that will be just the same, okay. So just it will be chi a1, chi b2 minus chi a2, chi b1, and again chi a1, chi b2 minus chi a2, chi b1, alright, and then you have to open these terms as done in the class, and so I'm again going with the same what we got earlier here. One minute. One minute. Okay, sorry, okay, yeah, this is, okay, okay, I guess I was already not zoomed in. Okay, I was already out, okay. So, okay, sorry, actually, I guess you can just reduce this size, okay, let us continue and whatever here we are now. Alright, so okay, so I guess I did I actually zoomed out, so some this is like small, and later on everything became big. So, okay, sorry about it. Okay, basically we will get the similar things. So let me just, okay, what we were getting is like this terms. So we will get the same psi of 1 and psi b of 2. Let us write. So basically, the same term that we got, we will get psi of 1, psi of 1. This time we will have alpha 1, alpha 1. Basically what will happen is that, as said in the class, all these terms will just become alpha 1, alpha 1, and we will have, so there will be no cancelling of the terms. So basically what will happen is we will have all the 1 terms, and there will be no cancelling of the terms. So what you will get is, we will get the same two terms that we are getting here. We get psi of r plus this, you can check, psi b of r, and you can get psi b of r. But what else will be there? There will be like these two terms, they will not have 0, we will have 1s. So because of this, again you can check that this one, psi of 1, psi b of 1, and you take psi of 1, psi b of 1 term, you take psi b of 1, psi a of 1 term. So they are just like complex conjugate of each other, right? And okay, so sorry, my mistake. Look at this. And done like these two terms. So this is like there is no plus, actually there is multi. Yeah, these two terms are same, psi of r and psi b, yeah. So yeah, there was no plus, which was multiply. So basically our two terms, they are just this coming as this multiply, and here also we will have this kind of multiplication, the same multiplication, and these two terms also, if you take, we will have a minus sign. Now we will have a minus term because the spins are same, which will be psi of r. We can take psi of r and psi b of r, and other term will be psi b of r, just complex conjugate of that, and psi a of r, and 1 into r dummy integral. So both these two terms, this second and third term, they will be same, right? Psi b psi a and psi a psi b. So we are getting something extra here, and that is because of the correlation. Sorry, because of time constraint, I am not doing all the questions, but this is, you can check easily, and some of the calculations are already done in the class. So here it is, electrons uncorrelated for antiparallel and correlation correlated for parallel spins. Okay, so there will be an exchange correlation. All right, let's move to next problem. All right. Okay, so the next problem, this is problem number 5. Okay, now what we have is, given a set of k orthonormal special functions and another set of k orthonormal functions, such that the first set is not orthogonal to the set it. Okay, sorry, actually we just have quite less time, so let's just do some other question. This is just for the orthonormality question, so it has similar problem as we done in the class. So let's just skip this question because we don't have enough time. Let us do some other question, the last other question. So I'm just skipping it. This is just related to the orthonormality condition of the this Satter determinant. So that question is just similar to orthonormality, but different wording. So because of time constraint, I am skipping that question. Now, okay, so let us do this one. So like consider the Satter determinant. We have k Satter determinant is chi I, chi j, and then we have some chi k, chi l. These are the different spin orbitals we can consider. So all these spin orbitals are orthonormal. Now we have to just show that kl should come like this. Note that the overlap is 0 unless, okay, and it is given here like the overlap is 0 unless k is equals to I and L equals to j. It means this spin orbital has to be same, in which case L will be exactly equals to k, and the overlap is a unity. And second, if k is equals to j, L equals to I, in which case this L will be just the minus sign and the overlap is -1. So this we will get from our result. So let us find this KL. Let us solve this problem. What we have to find is K and L. So what we have is, we need to find K is chi I, chi j, and this is chi k, chi L. Okay. So this we know could be written as 1 by root 2 chi I, chi j, chi I of the first electron, chi j of the second electron minus chi I2 chi j1, and this will be 1 by root 2 chi k1 chi L2 minus chi k2 chi L1. Alright, 1 by 2 chi I1 chi j2 minus chi I2 chi j1, and 1 by root 2 this kth spin orbiter chi L2 minus chi k2 chi L1. I can take 1 by 2 common here, and I can write chi I1 chi j2 and chi k1 chi L2 minus, this will be written as chi I1 chi j2 and chi k2 chi L1 minus chi I2 chi j1 chi k1 chi L2 plus chi I1 chi I2 chi j1 chi k2 chi L1. Alright, okay, I1 j2 k2 chi k1 chi L2 minus chi I1 chi j2 plus chi k2 chi L1 minus chi I2 chi j1 chi k1 chi L2 plus chi I2 chi j1 chi k2 chi L1. Alright, now we know, so what we'll have here, so this would be written as chi I1 chi k1 and chi j2 chi L2 minus chi I1 chi k2 and chi j2 chi I1 chi k1 chi j2 chi L2 chi I1 chi L1 and chi j2 chi k2 minus chi I2 chi k chi L2 chi L2 and chi j1 chi k1 plus chi I2 chi k2 and chi j1 chi L1. Alright, now this could be written as del of, okay, now since this spin orbitals we know they are orthonormal, so what we have is del of ik del of gl minus del of il here and del of jk minus del of il here, again we are getting del of il here, getting del of il here again, yeah, because of electron 2, and del of jk, and again I am getting del of ik and del of jl. Alright, now you can see these terms, this will be same, these two are same, so what we get is del of ik del of GL minus del of IL and del of GK. Right, and that is what we had to prove. Like this comes at del of IK, del of GL minus del of IL, del of GK. And then you can check that note that the overlap is 0 unless K is equals to I and L equals to J. So if K equals to I and L equals to J, that we are getting. And if K equals to I, L equals to J, then in that case we know K is equals to L, and what we are getting. So now if I just take the condition, if K equals to I and J equals to L, our KL is coming as, this will become 1 1 and this will be 0, so what we are getting is 1, which implies K is okay, so they are normalized and we can check that K is equals to L, okay, and the overlap is coming as unity. And the second case is given that if K is equals to J and L is equals to I, then this KL we can say that the first term will be 0, I equals to L and J equals to K, that will give us a 1 here, so we get minus 1, so we have minus 1, and if you check, so as written here, we will get L will be equals to minus of K. From the set determinant you can check by changing the rows, alright, and overlap is minus 1, okay, so this is also that we have checked. Okay, let us go to the last problem quickly, and we just have 3 minutes only. So yeah, so this is the last problem of the session. So let me just, okay, so we know the rules for this one. So basically what we have to do is we have to just verify the energies of the finite determinants by the inspection. So this is the question from Szabo and Austrian book. So we know the rules for this calculation. So what happens that an electron is in a special orbiter when A contributes as a core, it will contribute the core energy, and each unique pair of the electron special orbiters A and B contribute JB as the Coulomb energy, and each unique pair of electrons with parallel spin in special orbiters A and B contribute. Okay, so that will be the rules. So let me just so those are the rules. So let me just tell the rules that we have studied in the class. So like in electron in a special orbiter, A contributes as a core energy. Each unique pair of electrons in special orbiters A and B contribute JAB as Coulomb energy, and each unique pair of electrons with parallel spin in special orbiters A and B contribute minus KAB energy. Let us write the rules, and we will just solve 1 and 2 problems, and since and then you guys can try it out later. So since we don't have enough time now, so let me just write the rules that we have studied. So an electron in a special orbiter A contributes HAA as core energy. Okay, this is rule 1. Another rule is each unique pair of electrons in special orbiters A and B contribute JAB as Coulomb energy, and third is each unique pair of electrons with parallel spin. So we have to check the parallel spin in special orbitals A and B contribute minus KAB as exchange energy. Yeah, so these are the rules that we have studied, and now we can try to let us solve a few of the problems. So some problems they are solved in the class itself, like they are similar to the problems solved in the class. So for let us see here. So we can see that okay, using our rules, we can verify that for the first part, so there is one electron in the one, so it will contribute one core energy H11, and the second electron is in another special orbital 2, it will give another core energy H22. Then our second rule say that each unique pair of electrons in special orbitals A and B contribute JAB. So we have electrons in in special orbitals 1 and 2. So so they will contribute one J12, and they are parallel as well. So now they will contribute minus K12. So we have verified our first part. For second part, for B part, now we can see that okay, again we will have the same H11 we can get from a special orbital 1. Similarly we can get H22, and again we can get this J12 because we have one electron here in 1 and 2 spin orbitals, each unique pair we give. But now what we talk about the parallel spin part, that will give me a minus KAB term. Since these are anti-parallel spins, so we will not get an exchange term. So we are just getting 3 terms. Similarly, now in the C part, we will get one H11 from one electron and the one H11 from the other electron. So we get 2 H11 plus again one J11 because of both the 2 electrons. But again these are anti-parallel. The electrons are anti-parallel of opposite spin, so we are not getting any exchange term. In the D part, again now we get both will give electron 1 give H22, again second electron will give H22, 2, 4, 2, so we will have 2 H22 now, plus we will have a Coulomb term J22, but again these are an anti-parallel spin, so we will not get any exchange term. So this is also correct. Now E part, we will have again 2 H11 from these 2 electrons, and from these 2 electrons, and then we will have 1 H22 from this electron. So we get 2 H11, then you will get 1 H22, and because of these 2 electrons we will get 1 J11 as well. Now because of this electron and this electron, we will get 1 J12, and then we will get, because of this and this, we will again get one more J12. So we will get 2 J12, and then because we have to see the parallel spins. Now we have 2 parallel spins. We will have one will be in 1 and one will be in 2. So we will have a minus K12. So we will have one exchange term. So this is also correct. Now for the F part, from these 2 electrons we have 1 H22, 1 H22, so we are getting 2 H22. Then from this electron we are getting 1 H11. Okay. Now from this one electron and this one electron, when we get like 2 J12, so we are getting 2 J12s, and then from these 2 electrons we should get J22, so we are getting 1 J22, and then we have to check the parallel spins. We have parallel spins, so we get a minus K12. So this is also correct. And last, the G part. So again from these 2 electrons we get 2 H11, and then we get 2 H22. Sorry, from the single electron core energies, and then we get like 1 J11 from here and 1 J22 from here. Now there will be 4 combination, like there will be one combination of, you will see like there are 4 electrons, 2 in 1 and 2 in 2. So we'll get 4 combination for J12. So that we are getting 4 combination of J12. And then do we have a parallel spins? Yes, we have parallel spins. And then we have 2 up spins, one up in 1 and one up in 2. So that will give me 1 K minus K12. And then the down spins will also give me one more minus K12. So that's why we have minus 2 K12. So this is also correct. So using these 3 rules, we can easily solve these kind of problems. So that's all. That's all the problems for today. And thank you for your time.